Hey everyone, welcome to another video on elimination reactions, where we're just going to go back through a little bit of the content that we've already learned on eliminations, add a little bit to it, and mostly just get some practice. So we're going to start off with a review of E1, then we'll do a little bit of E1 mechanism practice, we'll review E2, and then we'll talk more about E2 Newman projections and how you can use a Newman projection to predict the products of a E2 reaction. So let's jump right in and look back at this same exact slide from the E1, so you don't need to write all this down. This is already in your notes from the previous video. So for an E1 reaction, we're going to have some kind of a substrate up here that has a leaving group. That's going to be the case for all four of the reactions, E1, E2, SN1, and SN2. In the case of E1, we not only have this molecule with a leaving group on it, but we have a base that is going to be weak. And so weak bases are going to look a lot like weak nucleophiles. That's why SN1 and E1 kind of go together. The way you can tell the difference between E1 and SN1 is because we're going to have this little triangle here in E1 reactions that represents heat, and that will help favor the formation of this pi bond. You don't need to know why that is, it just does. The thing that can happen with our E1 products is, depending on how many different beta positions we have, we can get multiple possible products, but there's pretty much always going to be one that is better than the other, or a major product and a minor product. So we talked about this one last time. If we can put the alkene more in the middle of the molecule with more groups around it, that is more thermodynamically favorable. So we would prefer that. We prefer to have more substitutions. So something like a di-substituted alkene is better than a mono-substituted alkene. A tri-substituted alkene would be better than a di-substituted alkene, etc. So when we're predicting the products of these types of reactions, you only need to show me the major product unless I clearly specify otherwise. But for a standard predict the products question, just the major product is all I need to see. So you do not need to draw me this minor product over here, because it may be formed, but it's going to be formed in a negligibly small amount. The mechanism for E1 starts off very much like the mechanism for SN1. First things first, our weak base can't really do anything, so our leaving group has to leave, form a carbocation here, and then you want to be sure to look for rearrangements, which we'll practice doing in a moment, before you actually do this step with the base taking off a proton. But then that is the next step after any rearrangements take place. Our base here, that's just a generic B for base, will pull off the proton, and then the electrons in that CH bond will fall down and kind of fill in that carbocation to make that new pi bond. Just a reminder that the rate law for this is a unimolecular rate law, just meaning that in our rate determining step, all that we have is this one molecule, and that's why we get the number 1 after the E, E1. E1 is a regiospecific reaction, meaning that we want to always form that most substituted alkene. If you have two different regions, like we did for this one, the region of our alkene over by this beta prime compared to the regular beta over there, the beta prime one is more substituted, right? So that's what we mean by different regions, is if you have those multiple possibilities and they are differently substituted, or they have more groups around them, then you want to go for the alkene that's going to be the most substituted, or have the most carbon groups around them, because it's thermodynamically the most stable. It'll also probably be giving you the most stable carbocation. So if you're needing to do rearrangements, you're going to want to rearrange to the most stable carbocation anyway, so you're always going to end up in a highly substituted region. This reaction is not stereospecific as far as thinking about whether that leaving group is on a wedge or a dash. It doesn't matter, because it's just going to leave, it's going to form a carbocation, and that's totally planar. And then, unlike a substitution reaction, we're not adding something else. We're making this pi bond, which is sp2 hybridized and flat, so it doesn't have sort of wedge dash R and S stereochemistry to it that we need to worry about. It's going to have cis and trans stereochemistry, but we can talk more about that in a bit. The only other thing to remind about here is that E1 is going to compete with SN1, and I mentioned this a little bit earlier. If you don't see this triangle sign, you probably want to assume you're doing SN1. If you do see that, it means we're heating the reaction, and that's why we are going to favor the elimination. So with that really quick reminder and overview, let's jump into a couple of practice problems. So for these practice problems, we're going to draw the mechanisms for each of the following E1 reactions and we're going to go through the mechanism in order to help us predict the product. This is a strategy that you can use while working on your homework or working through the exam if you want to. You don't have to draw the mechanism every time. but it may help at least to draw through the carbocation part so that we can check for rearrangements. So let's get started with this first one. We have a chloride, we have H2O, and we have heat. Here I already told you that we're going to be doing E1, but make sure that you're looking out for these key signs here to tell you that we're doing E1 if I weren't to have told you about it ahead of time. We have a weak nucleophile, water. We have the key of heat here, which tells us that we are going to be favoring elimination, not substitution. So for the very first step of our E1 mechanism, we're going to let our leaving group leave with its electrons like so. And then we are going to say that makes us a nice carbocation. I'm going to go ahead and adjust this arrow here to make it a reversible set of arrows because all of these steps are reversible. I'm not going to be super picky about it, but just so that you know, they're all reversible. I'm going to also cheat a little bit and copy this over, but remove our chloride and say, okay, there's our positive charge. So you'll note that I just dove right in and got started with this mechanism. I didn't do any of the beta position identifying stuff that we practiced in the previous video. You're welcome to do that at the start, but I want to offer you a different way to approach E1 mechanism drawing, where we just get started with the mechanism. And then when we get to this point where we've made that carbocation, before we even think about beta, et cetera, we want to think about rearrangements first, right? So let's now analyze where our carbocation is. It's at this carbon here, which is secondary. But hopefully you all are eyeing up this position down here, which is tertiary, meaning it has a single tertiary hydrogen on it that we can label here in purple, that we can use to rearrange to a more stable carbocation. So let's do that first, because if you can rearrange to a more stable carbocation, you must, absolutely must. And one thing I noticed grading your homework on rearrangements for other types of reactions, a lot of y'all are drawing this, and that is no good. I don't want to see that arrow on the exam, all right? What I want to see is the arrow coming from the electrons, right? So it has to come from these electrons in the bond. You're always welcome to draw them in, but you also don't have to. It has to come from there, because it's not just the proton that's going, it's the proton and its electrons. So it has to be an arrow that looks like this. If you are practicing on the homework and you find that these arrows get a little bit messy, try just drawing bigger, or if you need to switch up to pencil, to practice drawing and erasing until it looks clear and legible, right? So I want to see your arrows looking like this for any kind of hydride shifts that you need to do. So once we've done that shift, what is this going to look like? I'm going to copy this carbon framework again, except that that chlorine is obviously gone, far, far gone at this point. And we've instead moved our positive charge down there to that tertiary carbon because we moved that purple former tertiary hydrogen, we moved it over. So now it's sitting on that secondary carbon that we started with. So now we've got this really great stable carbocation. It's happy, it's where it wants to be. And that means that the reaction can actually continue to proceed now, and we can use water as a base to pull off the proton and make a new alkene, right? But which proton do we want? We better consider that. Now is the time, if you want to use this strategy, you're welcome to. Now is the time where I'm going to start thinking about which positions are alpha, beta, and think about which proton then we want to pick off. So the place where your carbocation is, in the case of this method, is your alpha position, right? Because we know we need to be one away from that to form the alkene by kind of jumping over those electrons and filling them into the positive charge. So we still have to go one away from there. One thing that I like about this method of kind of waiting to form your carbocation first is that you will be able to catch rearrangements. Now, not every question am I going to give you will have a rearrangement, but a lot of them will. You're definitely going to see that on the exam. So if you use this method where you kind of wait it out and see where the carbocation ends up, you get a better idea of where the beta positions are. If we think about the first method I gave you, it's fine, but that would put our alpha carbon up here, right? Again, which isn't the end of the world, except that I can't draw a good alpha today. It's not the end of the world, but we might miss out on that rearrangement if we were just really working fast and predicting the products. We might predict a alkene going up here because that's a possible beta position, or down here because that's a possible beta position as well, right? And so those answers might be correct, but they also might not necessarily be correct. So that's why I want to look at this method to give us a little bit more insight after we've done our rearrangement to give us the best possible product and make sure that it's all super clear. So let's identify, we've identified the alpha position now. Let's identify some beta positions. So beta could be here, any carbon that is one carbon away in any direction. So we have 3 possible beta positions available to us, but are any of them the same? Answer the video question, are any of these beta positions identical? Yes. So the kind of top one here and this one off to the right side are identical because they're both just 2 carbons. Here's 1, 2 and 1, 2. So they're identical groups. And that means that we really only need to consider one of them at a time. The other one is redundant. Even though it's a beta position, it would give us the same product. So I'm going to go ahead and get rid of that one, right? But then this one out here, right, kind of pointing to the left instead. Now that's definitely different because it's just a methyl group. So now we have beta and beta prime. Okay, so based on these available beta positions that both have hydrogens on them, right? This one is drawn in purple because that was our shift hydrogen, but there are other hydrogens there, and there's the methyl hydrogens down here as well. Based on those 2 positions, which proton do we want to take off to give us the best possible alkene or the most substituted possible alkene? Do we want to use the beta protons or the beta prime protons? Hopefully you can see that if we were to pull off the beta prime protons, we would start making a double bond there, which is okay, but it's what we call a terminal double bond. It means it's sort of hanging off the end of the molecule. And that means that it, at most, can only have 2 substitutions, right? The carbon groups on the other end. But if it's at the end of the molecule, there always have to be at least 2 hydrogens left over at that spot. So that's not the most substituted product that we could get. If we were to instead choose the beta position instead of the beta prime position, we would be able to get an alkene kind of here. Now that has 3 substitutions, right? 1, 2, 3, and that will give us a more highly substituted alkene. So we want to use that proton instead. So it might be this one that's drawn in purple. It could also be the one that's, was just there to begin with, right? Because there was one here in our starting material, we just didn't draw it in. It doesn't matter which one you pick, right? Because either one can align with the carbocation. This is not stereospecific, like we said, so we don't have to decide between either one. I'm just going to pick one. So we'll go ahead and bring water in at this point as our weak base. We'll use it and its pair of electrons to pull off one of these hydrogens. So for this one, you want to make sure you're picking up the hydrogen with one arrow. Use your other arrow to show that CH bond breaking and falling down along that alpha to beta bond to form our final product, which is going to look a little something like this. So if you're paying careful attention, you'll notice that this product is one that I kind of quick predicted from over here when I was talking about looking at this as our alpha carbon and this as a possible beta carbon. That ended up being the case, right? Where we form the alkene between those 2 carbons. It's just that alpha and beta happen to be sort of switched because of their rearrangement. So in the case of this question, it might feel a little redundant what we did here because we had our leaving group leave. We then moved a proton up here, right? Again, don't draw your arrows like that. That was a bad arrow. And then we pulled that same proton off and formed a double bond there. So it feels like extra steps, right? And in this case, it didn't actually make a difference whether we did the original method or whether we did this rearrange your carbocation and then look for alpha beta positions method, because it just ended up in the same place, right? And I should say here also, just to reiterate, that if you had chosen this beta position down here, that definitely would not be an incorrect answer. You would just maybe have drawn the product to look a little bit different. You might have drawn this product instead of that, but they're actually exactly the same. You just have to turn one of them around and it'll be the same thing as the other one. So don't worry if that's what you got for this one. That's totally a correct answer as well. But just because it didn't matter for this one doesn't mean that it's not always going to not matter. Sometimes it's going to matter. So let's look at an example where it turns out it's going to matter. And that's this last one down here at the bottom. I'm going to move this up a little bit. And let's start going in with the same method that we did here this time, where we're not going to think about alpha and beta until we lose our leaving group and do any rearrangements that we would need. So first things first, we've got our good leaving group here, iodine. That's going to leave with its electrons. I'm going to go ahead and fix this arrow to make it reversible. There we go. And then we're going to just duplicate this carbon framework here. We will have arrived at this ring with now a positive charge at that position where the iodine just left. Okay, seems fine, right? Let's identify and see if we need to do any carbocation rearrangements. We're at a secondary carbocation here, but again, this is the kind of thing you want to be looking at. If you're at a secondary position, but it's next to a tertiary position, that means we have a tertiary hydrogen, and that means we need to rearrange to make a tertiary carbocation because it's going to be the most stable. So let's go ahead and do that here as well. I'm going to use, again, the electrons in the bond, not the atom, but the bond itself has to move over and attack that positive charge. And then we will get something that looks like this, where we've moved that purple tertiary hydrogen over. And then we get a positive charge at that position, sort of at the top of the ring. So there's our nice, stable tertiary carbocation. We really like that. We're happy with it. And now we need to think about the alpha and betas to identify where we might eliminate to. So here's our alpha position. That is right where the positive charge is. And then we have several beta positions, right? We've got beta up to the top, we've got beta over here, and we got beta over there. So go ahead and answer the video question. Are any of these positions the same? Nope, none of these positions are identical. We have a methyl group up here at the top. We have kind of another tertiary position over here on the side, and this one is secondary. So they're all different and unique. So we can't get rid of any of them just yet. We have to think about all of them. So here's, we'll call this one beta over on this side. This one will be beta prime over here, the secondary one, and then the top one will be beta double prime. And you can give these more creative names if you want to. I'm just using alpha and beta because that's kind of the standard for chemistry. So let's analyze all of these positions and think about which ones would give us the more stable resulting alkene with more substitutions. So if we start at beta double prime, just because that's where we were up at the top, if we think about that being a methyl carbon, right, it has a set of primary hydrogens. And if we were to kind of just do a real quick sketch in of what that double bond might look like, it would be there. And so that's okay, but again, it would have 2 hydrogens up here at the top and only 2 carbon groups. So that would give us a di-substituted alkene. So you're welcome to make notes about this kind of thing as you go to remind yourself, especially if you've got 3 different positions, you may want to make some notes so you can come back to them. So we'll say that this would give us a di-substituted alkene up at the top, and that's, you know, maybe not the greatest. So let's keep going, see if we can find something better. If we were to use the beta prime over here and pull off maybe that purple hydrogen or maybe the other one that's there, we would get an alkene that goes kind of there, like so. And now let's count up the substitutions on that. We'd have this group here at the top, we'd have this group on this side, and we have this part of the ring on that side. So that would be a tri-substituted alkene. And that would be the one that we would kind of have predicted, right? Because that's where the leaving group was. We're sort of thinking about making an alkene on that side anyway. So tri-substituted is pretty good, but let's just check our regular beta as well and think about that. If we were to pull off the proton that is here, right? So it can be easy to forget. So feel free to draw those protons in at any time. If we were to pull that one off, we make an alkene right there. And then if you count the substitutions of that, we have 1, 2, so 2 methyl groups kind of on the same side of that alkene. And then we have a ring over here and we have ring over here. So this is actually an example of what would be a tetra-substituted alkene. So the fact that we could make a fully 4 times substituted alkene means that we absolutely super duper want to do that, because that's going to be the most thermodynamically stable, and we always want to form the most stable possible product. So even though the tri-sub is pretty good and it was at the position where our leaving group left from, that's actually not the one that we want to choose. And we also definitely don't want to choose the di-substituted because that was by far the least exciting or the least good possible position out of all of these. So we're not going to choose the tri-sub either. We're going to stick with the tetrasub beta on that side. So let me get rid of these little dot annotations here and we'll draw in that hydrogen so that water can remove it. And then we'll bring in water. Push our arrows just like we have been this whole time. Use the water to attack that atom. And then we have to break the CH bond like so and let those electrons kind of fall down along the alpha beta bond to form our alkene. And so then our product at the end of this reaction will look like this, where we've now made a tetrasubstituted, super thermodynamically stable alkene. And so this is an example, like I said at the beginning, where it does matter that you do the rearrangement and then analyze for your beta position. Because if you just make this carbocation and you think, oh, well, it's going to rearrange, but it doesn't matter because we're going to pull the proton off, you would have picked the wrong product, right? You would have instead have predicted this to be the product. That's a little sloppily drawn there, but the point being that that's not the most substituted possible alkene. So we have to be a little bit more careful and discerning about where we form our carbocation if it needs to rearrange, and then which positions we want to pull our beta protons from. So I think I said this in the beginning of the first video, that sometimes finding those beta positions and deciding between them can be the trickiest part of doing our eliminations. So practice on this more with homework and some practice problems coming up to the exam and see how it feels. Let me know if you have any questions about it. So with that, let's shift gears a little bit from E1 to E2. Here's our little review sheet from E2. Again, this is the exact same stuff from the previous video, so you should not need to write any of this down. It's probably all already in your notes. For E2, we have the same idea that we have some kind of a carbon-based molecule with a leaving group on it. And then instead of a weak base, we have a nice strong base that is oftentimes going to be very bulky as well. And that's going to give us a certain type of alkene product where we are going to, we'll talk about the regiospecificity here, favor, instead of that more substituted side, the less substituted side. Again, multiple possible products will usually happen or be possible to happen. And unless I tell you to show me all of the possible products, you only need to list the major product. So if that's ever unclear, please just ask. As for the mechanism, this happens similarly to our SN2 mechanism where it's all going to happen all at once. We don't have any steps. It's a single step mechanism where everything goes down all at the same time. So our strong base comes in, picks up the proton by attacking it directly, and then we use those CH electrons to fall down along our alpha to beta bond. That provides some motivation for the leaving group to leave all in one fell swoop, and we get this product here. The rate, once again, is determined by the concentration and therefore just sort of presence of both of these two components at the same time. We have to have our electrophile here in conjunction with the base, all in the right place at the right time. And they also have to have a sort of specific arrangement in space. So we talked about the regiospecificity here, that we want to get the less substituted one. That has to do with the bulkiness of our base. But then when it comes to arrangement in space, we have to have a very specific anti-arrangement of groups in space. So the hydrogen here is to be anti to our leaving group. We'll get more practice looking at that in just a moment. Just want to quickly reiterate that E2 doesn't so much compete with SN2, not in the same way that the sort of 1 reactions do. E1 and SN1 are always competing with one another. But E2 and SN2, there's a little bit more of a difference, so you don't have to worry about that quite so much. But what you want to be looking for to say, oh yeah, that's definitely E2, you want to be looking for the bulky, strong base. So something that has a bunch of branchy carbons on it and also a negative charge. So otherwise, if it doesn't look very bulky and you have a secondary or primary leaving group, you're probably doing SN2. But again, hang on to the next video for a little bit more practice on discerning between all 4 of these different reactions and mechanisms. So now let's talk more about the stereochemistry and sort of stereospecificity requirements of this reaction. So we said already that a specific arrangement in space is required, and then we called that arrangement anti. So what does it mean to be anti? Last time we defined this as opposing or 180 degrees apart on sort of opposite sides. So we want to be able to think about what that might look like in a variety of different ways. So we did, kind of one quick example of this in the previous video about just sort of looking at a flat projection like this and identifying where an anti-proton was, a proton that is in an anti position to our leaving group. So all that means is just that it's got to be 180 degrees apart. So let's go ahead and try these ones together and see how that goes. If we have this first molecule here on the left, we've got our leaving group and it is in this position here. Doesn't so much matter where it is on the molecule for now. What we just want to think about is its arrangement in space based on this bond there. So that is a dashed bond, which kind of means that if you're picturing your screen as totally flat, it's kind of like fading back into the background behind some, some fog. We've had some foggy mornings. Think about it like that. There's like a bit of a curtain of fog in front of it because it's behind, right? So we need to think about something that's going to be 180 degrees away from something that is behind. So if you had something that was behind something else, you wanted to say what's on the opposite side of that, something that's in front, right? So when we're looking at these hydrogens here, right, those seem to be the ones that I've drawn in for some specific reason, right? I wonder why that is. Usually if I draw something in, you may want to be thinking about it and paying attention to it. But let's also just remind ourselves that we have those hydrogens specifically at that beta position. That's why I've drawn them in, because they're beta hydrogens. We need beta hydrogens to do an elimination reaction always. So between those two beta hydrogens, let's give them some names, shall we? Between hydrogen A and hydrogen B, which one is 180 degrees away from our leaving group? The one that is in front, like we were saying earlier, is HA. So we're going to circle that one because it is 180 degrees away from our leaving group. Now, HB is not in the right position. We'll talk about Newman's and how we can rotate to put it into the right position, but more on that for later. One thing that you also might be asking yourself is, Grace, what are you forgetting about these protons, that beta position? This is a beta prime position because it's different from the other one. What about those protons? Aren't they fair game? Yes, they are absolutely fair game, and they are probably actually better suited to an E2 reaction. Why is that? Why would I favor removing a beta prime proton over these two beta protons? It has to do with substitution. Our beta position over here is secondary, so a little bit crowded, but not super crowded, but beta prime is primary, right? So that's very not crowded, and that means it's going to be easier for a big bulky base to get in there and pick off a proton. So yes, absolutely, these would be a better choice. Let's in fact draw in these protons, but think about which one is going to be anti. It's sometimes we don't always draw in these methyl protons like so, because they're all equivalent and we don't think too much about their arrangement in space because it doesn't matter. And for even once we pull this off, we're going to make an alkene where it doesn't matter which one we pull off because the other two will still be remaining. It won't have any stereochemistry around it because it's at the end of a molecule. It's a terminal alkene. But just for the sake of practicing, between these three methyl protons here, let's circle the one that is 180 degrees away from our leaving group as it's drawn right now. Go ahead and make a prediction. And again, if you're thinking, okay, I'll look at what we did for that first one. The leaving group is still dashed, so we also would want a wedge on this side. Yep, you're exactly right. We would want that one there that is wedged. So that's the idea here. Let's move on to another one that's maybe a little bit different looking here. We have our leaving group at this position right here. And then we have some hydrogens at this beta position over here. And we also have this sort of wedged group. That's an isopropyl group. You don't need to really know that, but that's just what it's called. You'll hear me use it a lot. Coming out of the page as a wedge, and then we have the other hydrogens like so. Okay, so let's put some names to these again. Now, between those two, A and B, which hydrogen is currently in the anti position with respect to our leaving group, HA or HB? Now this one's a little different, isn't it? Because from what we've seen mostly so far, we have a leaving group, and I'll often put that leaving group at a wedged or dashed position to show where it is in space. But I didn't do that here. This leaving group is just, it's got a plain straight bond. It's in the plane of the page or the screen. So how do I know it doesn't have a wedge or a dash? That's true. And it doesn't need one either, because you just have to look for something that's 180 degrees away. It's not always easy to see 180 degrees away when you are looking at something that's on an adjacent carbon. But if we just kind of follow a line here, I'm going to just kind of trace this line from that carbon to the leaving group and extend it a little bit. That's a 180 degree angle. And the angle of this kind of mimics this angle here, right? So that's all I'm trying to show you, is that this HB, even though it's kind of boring, it's also in the plane of the page. So that's actually good. That means that HB is sort of aligned with it, right, in the same plane, but it's pointed the opposite direction, sort of, if you look at it with respect to the page. The leaving group is pointing kind of down to the bottom right-hand corner, and HB is kind of pointing up to the top left-hand corner, which are 180 degrees apart. So this one may be a little bit trickier to see, but hopefully that makes sense why we would want to choose HB and not HA. Again, we could draw some Newmans and rotate to put HA in the right spot, but more on that on the next slide. Let's do this very last one and identify where our leaving group is. It is right here at that alpha position. And then we have this hydrogen over here. I put this fluorine in here just as kind of a little red herring, right? That's not a leaving group or anything. It's just there to fill up that position, essentially. So let's think about our beta positions. If we looked over here, this beta position cannot be because there are no hydrogens there. There's too many methyl groups, so we don't want to think about that position. But over here, we do have one hydrogen at this beta position. So you're thinking, well, I've already ruined the surprise, right? That's the one that you circle. Well, let's look a little bit more carefully at it, shall we? Our leaving group here is on a wedge, right? So that means it's coming out of the screen at you, which means the hydrogen we want needs to be 180 degrees away or kind of pointing away from you behind the screen. But we don't have that here. If we look at this hydrogen, it is also a wedge. That means that both of them are pointing out at us. So their angle between them, you don't need to know this, but it's probably only 60 degrees apart and not 180 degrees apart. It needs to be a dashed hydrogen, but we don't have that. So can we do elimination here? Is that even possible? Yes, but we're going to have to draw some Newmans first. So this one was a little bit of a trick question, but we can't use that hydrogen as is. We must rotate first. So now let's go in and talk about some Newmans, because we drew some last time, but I didn't give you a whole lot of skills to use the Newman to quickly predict what the structure of the product would be. So I want to go ahead and re-practice that using some of the examples from the previous video. So I think this was the first one that we looked at and trying to differentiate between these hydrogens A and B. Let's give them again some names. A and B. So thinking about what we just did, let's do a quick re-practice of that. We know where our leaving group is here. We have hydrogens B and A. Which hydrogen right now is already in the right position before we even bother drawing the Newman? That's right, it's HB, because our leaving group is on a wedge here. We need the hydrogen to be on a dash to be 180 degrees away. Let's draw the Newman to convince ourselves of that and to help us predict what the product would look like. So if we decide to draw our Newman coming in from this direction here, we're going to end up with the same Newman that I drew for the previous video, but I just want to go back through redrawing it to give you a moment to think about practicing drawing your own Newmans. If they felt comfortable, I think a lot of you did really well with Newmans on the last unit, so good job. If they feel comfortable to you still, great, then you maybe don't have to practice this as much, but it's also a good chance if they weren't super comfortable to practice them again. So we have our dot here in the middle to be that alpha carbon. Actually, we could leave it as a blue dot, right, to show that that is the alpha blue labeled carbon. And then again, trying to picture your own face here if you're having trouble with this. Picturing your own, kind of face here. There's your nose and your mouth. See, that's why these get really creepy, because I'm also terrible at drawing faces. But if that helps a little bit to picture your head there, this big group is right up above your head. It's kind of pointed at your forehead. So that's why we put that straight up, like so. And then we know if that's the sort of straight up position that the other two have to be coming out at these sorts of angles, but don't leave them there without labeling them. One of them is going to be our leaving group, and that one is going to be the one, if you position your face that way, it's kind of pointing out, and so it's toward your right hand, so it's going to be on the right side. And by extension, the other thing that's back here that I didn't draw in for us is a hydrogen, so we can just leave that there. Okay, and we're halfway done with the Newman. On the back carbon, if we look for the thing that's in the plane, right, that's this methyl group. It's kind of pointing downward toward our chin over here. So we're going to point that straight down. And then we just have HA and HB, which must be at these positions up here because this is a staggered conformation. Again, review all this if it doesn't feel comfortable. HA is, again, if we picture ourselves, I'm literally, you can't see it, but I'm literally turning my head to the side and trying to align it with my iPad to do this. That's how it works best for my brain, but whatever works best for you. The HA, again, is a wedge that's kind of sticking out, and that's on our right side. So there's HA, and here's HB. So just like we did last time, we can think about that 180-degree line on our Newman. That's how we can see that HB aligns with our leaving group perfectly. So let's use this Newman to predict the product of the reaction as is, and then we'll do that rotation that I've been talking about. So when you go to predict the product of an E2 elimination using a Newman projection, it's kind of nice because you can just do this little shortcut and then fill in all the groups around your product. So what I'll do here is, I'm actually going to copy this over first because we're going to need another one of them later. But you want to draw your line, right, between your hydrogen that's anti to your leaving group and the leaving group. That's your elimination line because those things are not going to end up in your product. So those ones are going to get eliminated. And then based on the positioning of that line, you can see that you'll have two things on the top side of that line, and you will also have two things on the bottom side of that line. And so the things that share the same side of your elimination line are going to end up on the same side of your alkene. So if you just draw in an alkene like this, then you can basically fill in all of the things around it, and that's your product. So you're welcome to do it based on something like this and kind of recopy this and adjust it if you want to, or you can do this method where you literally just draw a double bond and then you put some stuff around it. Whichever works, depends on your learning style. So if we take this isopropyl group, or that 3-carbon group, and HA and put them on the same side, we get something that looks like that. And then we have to put H and CH3 on the other side as well, but just make sure that you keep in mind which ones are bonded to the same carbon. So if you kind of follow along the Newman here, we got this 3-carbon group, and if we follow it along, it has to be connected to the same carbon that that H is, that unlabeled H. So the unlabeled H has to be on this end of the alkene, and by extension, the CH3 has to be. So that's the product that you get from this elimination using this Newman projection. So these groups end up on the same side of the double bonds, right? So there's the one side, that's kind of the blue side, and then we have the green side over here. So this is a way that a lot of students, I think, find quick and easy to predict products. If you have to draw a Newman, you won't have to draw a Newman for every E2 elimination, but if you do, this is a quick way to predict your product. Now, before we move too far on, let's think about doing a rotation here to switch up that back carbon, like I was hinting to at the end of our last video. What I want to do is rotate so that HA could be eliminated instead. So we're going to do this rotation essentially, rotate the back carbon 120 degrees around. So in order to do that, I'm going to just erase these labels and fill them back in. So we said that we wanted HA to be at this position. And it may help to look at this existing Newman projection to remind yourself what was where. If we moved HA to here, that's good. Then we would need to move HB to the bottom position down here. And this CH3 group would have to go over here and take the place of HA. That's how I like to do these rotations with Newmans. Again, do them in whatever method works for you, but this way you can be sure you didn't accidentally flip something around by removing your labels and trying to draw them back in. Okay, so now let's see how that rotation has affected the product that we get out of this reaction. So here's our elimination line. Now, if we think about what's on the same side of the line here, we've got those two groups are kind of on our blue side and these two groups on our green side. So again, you can just draw a double bond like so, and then fill in around it. So I'm actually going to draw, because our front carbon didn't change, I'm going to draw the same half here, exactly the same as it was in our first product, because it didn't really change. Right? So that 3 carbon group and the hydrogen on the front carbon, no problem, like so. But then we have to think about what's on the same side of the alkene as them. So on the same side as this 3 carbon group, we have our CH3. So that's here. You can label it or not, doesn't really make a difference. And then on the same side as our other hydrogen, we have HB that didn't get eliminated this time. So just to make it consistent, I'm going to erase that CH3 because it looks more similar to this first product that we drew. And again, if we think about the blue side now has these two groups on it, and the green side has those two groups on it. So we can see that these are definitely not the same product. So it does make a big difference what is in the anti position to our leaving group, right? Because you get 2 different products, and we need to know about that. If there are 2 possible products and I want you to draw both of them, I will definitely give you a hint to do that. Otherwise, if I were to give you a question like this, there would probably only be 1 hydrogen that could get into that anti position. Like if I were to have made this some other group instead, like I made this another carbon, then there would only be 1 possible proton that you could pull off, and that would be the one that you would want to use. So anytime that I would ask you for multiple possible products, I will give you a very clear instruction to show those to me. And again, if there's ever any confusion, just ask. So thinking about the fact that these are 2 possible products, right? But they're pretty similar. I'm just erasing those circles so we can get a better look at them. They have all the same groups, other than the fact that HA and HB are not quite the same just because we gave them names, but they're both just hydrogen, right? So if we think about that, what's the relationship between these 2 products? So this was a little bit of a throwback to earlier in the semester when we talked about how compounds that are similar are related. So we can kind of go through our mental flow chart here to check. If we think, okay, they have all the exact same number of atoms, right? You can go ahead and count and double check me that this is the same number of carbons between each, the same number of hydrogens. So they are not totally different molecules. Are they connected differently based on which groups are connected to what parts of the chain? No, because at this sort of front carbon here that we were talking about, there's an isopropyl group and a hydrogen. And at the back carbon, in both cases, there's 1 hydrogen and 1 methyl group. So they're not differently connected. There's an alkene in between each of those carbons, but it's otherwise all the same. So then you have to ask yourself, do we have a double bond or a ring here? Yes, we do have a double bond. And then we have to think about cis and trans stereoisomers. So the correct answer was that these are stereoisomers of one another that happen to be a trans and cis pair of stereoisomers. So again, trans meaning that we have this large group or the most important group on the opposite side from our other most important group, or cis on the other one, meaning that both of those largest groups are on the same side. So just something to think back to from our previous unit. All right, let's do one more. This is again another example from our previous video, but let's actually go in depth, practice drawing the Newman, practice rotating, and thinking about the differences in products. So again, we have our alpha carbon here, what has the leaving group on it, and then we decided in the last video that we wanted to use this beta position because this one is possible, but it's a little bit more bulky. So we wouldn't favor eliminating there because it just is a little harder for a base to get in and pick up the protons. We would rather use these ones over here. So let's give those some names as well and take a look at where they will be on our Newman. So we're going to draw, looking this same direction, down to our alpha carbon here in the middle. And let's fill everything in. So this also happens to be a staggered conformation. I'm not going to do anything tricky and give you an eclipse conformation for the exam because you need a staggered one to have that anti-arrangement. And again, we have this sort of thing here in kind of the plane of the page. It's right above toward our forehead. So that's going to be coming straight up. That's 1, 2, 3 carbons. Always be sure to count if you're not 100% certain. And then we have 2 other things coming off to these sides, but we want to make sure we label them before we walk away. If you turn your head again, that sort of wedge isopropyl group is coming out toward the right. So I'm going to put that over here. And then our iodine leaving group is pointing backward or kind of to the left side there. So there's our leaving group iodide. And then if we look at the back carbon or our beta carbon, we have something pointing down in the plane of the page, and that is going to be this methyl group, right? Because it's kind of pointing straight down toward our chin as we're looking at it. And then we have HA and HB. I'm not sure if I labeled these the same or not as before, so just always triple check. If I turn my head and think HA is a wedge that's pointing out, so that is going to be on the right. And HB, therefore, must be on the left. So there's our Newman. Again, let's do our product predicting, and I'm going to move this up and copy it over so we can rotate later. Before I draw all of these marks on it, here's our elimination line. And then we know which things are on the same side and which things are on the opposite sides. So on the same side here, we have HB with our 3 carbon linear chain. And on the other side, we have a CH3 with our isopropyl or sort of not linear 3 carbon chain. Draw yourself an alkene. And then on the front carbon, we have that 1, 2, 3 chain. And that is also attached, again, sort of do this little tracing if you need to. We have that 1, 2, 3 carbon chain here. It's attached to the same carbon as that isopropyl group, like so. So that goes here. And then on the back carbon, we have HB and a CH3. We know that HB is on the same side as our 3 carbon chain. And we know that the CH3 was over here with this kind of Y-shaped isopropyl group. So we get that. I'll put in our circles here. These groups were together on the blue side, and these groups were together on the green side. So hopefully this helps you feel a little bit better about how to predict the product once you've translated. So, we have this sort of molecule, and that maybe looks pretty familiar by now, I hope. But when you translate it to something like a Newman, it sort of loses a lot of that chemical meaning that we're used to looking at. So hopefully this gives you a really clear and concise way to translate your weird Newman back to something that looks more like a flat molecule that we're used to. Okay, so we did that elimination. We eliminated HA. I want to now do the rotation again to show what the product would be if we eliminated HB instead. So what we'll do is we'll move HB over this way so that we get it at this position here. So this will be HB. And then if we do that, that means HA has to come down to the bottom here. Oops, it's not a big A, it's a small a, HA. And that means the CH3 has to go over to the left side. Okay, so there we go. We've adjusted our Newman, and now we can draw in our elimination line again. Like so. Now we can see what groups are on the same side. If we circle them up here, we got those 2 things together on the blue side and these 2 things together on the green side. So draw yourself an alkene and fill everything in. Again, we didn't change the front carbon, which happens to be this one, so I'm going to draw that exactly the same. But if you're not sure, just check yourself. Isopropyl group, like so. And then we know that HA has to be on the same side as that Y-shaped isopropyl group, and the methyl group is on the same side as the linear 3 carbon chain. So again, we'll fill in our colorful circles. That's our blue side, and this is our green side. So there we have it. We have the 2 possible products because we have 2 beta hydrogens available to us. And again, if we remove these circles so that we can see a little bit more clearly, and then think about the relationship between these 2, those are also a pair of stereoisomers. So I don't think I mentioned this in the previous example. I'm calling back to the stereochemistry unit, but I'm not going to ask you to actually define cis and trans on any of these problems. You should just know that they are related to one another as stereoisomers. Okay, So with that, I have basically the same stuff for you to review and practice this time around, that we need to be thinking about these mechanisms, identifying weak versus strong bases, thinking about the beta hydrogens and the regiochemistry of eliminations. Particularly, try out the other method that we practiced today for E1 to make sure that you're getting the best regiochemical outcome. And for E2, practice your Newmans again and try this new method for predicting the product after you've used a Newman projection. And then if this is all feeling comfortable, our next video is going to be the sort of the big comparing end all be all, where we put all the pieces together, show how they're similar, how they're different, and do a whole bunch of practice. So stay tuned for that. If you have any questions as you're working and practicing, just let me know. Post a comment here, post a comment in the discussion forum, send me an email, or stop by office hours. Until then, take care.